today's lecture is like interview, so it's 4 proofs basically. Okay, but the first one is so it's kind of the proof is evolving. The first one is the same type of proof, but it is evolving. So you can see that how this proof becomes more and more complicated, and this is exactly the method which is used to prove that 4-color theorem, and now it is used to prove several other things like the Galai conjecture, Morse conjecture, a special case of Jezier's conjecture, short proof of Bloch theorem, which we will see, and Orr's conjecture is not, some of these conjectures are not just one conjecture, it's a set of conjectures. Like there is a k in the conjecture, and if you vary k varies over every positive integer from 3 to onwards. So even solving one was challenging, and using this technique we have solved all the cases almost, or we got very excellent numbers. Planar graphs are 5-color. So imagine that this statement is, imagine that this too dusty, this statement is false, so and assume the contrary, and take a minimal counter example. Yes.
Different people, what is?
G. So minimum with respect to number of vertices. Okay. So here I will speak about a small technicality. So whenever we say minimal, we usually take number of vertices or number of edges or number of vertices plus edges. Sometimes we say subgraph inclusion, but as researchers you should know what minimality means. So when minimality means whatever you are taking this minimality over, or with respect to whatever things you are considering, that has a partial order. Somewhere there is a partial order, okay? So you have to check, you can make this very, very weird or something strange, but you have to make sure whatever you are saying that gives a partial order, and then with respect to partial order you can always take minimality. So that is important. Sometimes I have seen something extremely weird, like either it has to be a subgraph or the number of vertices which has degree more than equal to 3, that has some condition. So in those cases what you can do, you can add many degree 2 vertices and it helps you. So you can get a graph which has more vertices than your graph, but it is smaller than your graph in that partial order. So be careful what minimal is. Okay, what it means is minimal counterexample. So G has the minimum number of vertices, but it is also so G is a counterexample. Among all counterexamples, G has minimum number of vertices. Okay. So now what do we know? G has a vertex of degree less than equal to 5. This we have proved yesterday. Okay, because G is planar. So anyways, I will say something like, what does it mean? It means G is planar, not 5 colorable, and any subgraph, proper subgraph of G is 5 colorable. So do you see that G is actually a 5 critical graph, right? Well, not proper subgraph, but proper induced subgraph. Or if I do this as agents, I don't want to do that. Proper induced. Okay? Because I can delete edges, but still it may be not 5 colorable because my counterexample is on number of vertices. Okay? So, anyways, so this is what it means by enumerability. Okay. Now, V, let V be a vertex of minimum degree in G. Okay? That's all I will write about the proof. Everything else is drawing. So V is a minimum degree vertex in G. What can be the degree of V? Can it be 0? It has to be connected. Why? Because otherwise you delete V. The rest of the graph is 5 colorable. You add V, you color it with whatever you want. In fact, if V has degree 4, this is the rest of the G, then what you can do is, you can simply delete V, you can delete V, and so what is this? This is G minus V. Okay? So just take G minus V, because G was minimal counterexample, this guy is 5 colorable, right? And now you add V back. V has degree 4 or less, is what I am saying. So I have used maybe 4 colors here, but the 5th color is remaining, so I can always color V. So if these are to write it technically correctly, I can write, suppose that V's neighbors are V1, V2, V3, V4. So choose, so I can write choose C of V in my color set C, or I think our definition of coloring was 1, 2, 3, 4, 5. K coloring was these integers minus C of Vi such that I equals to 1, 2, 3 and 4. Right? You can always choose them. So I know the minimum degree vertex cannot be at most 4. But I also know the minimum degree vertex should be at most 5. So there should be a vertex of degree 5 in G. So from here, what I deduced is G has a degree 5 vertex. So I should not erase, right? I try to do that.
Yes.
Okay. So here, I think this is enough. So this is V. This has degree 5. Let's say V1, V2, V3, V4, V5. Now I will do something important, which many times we tend to skip because it has like, already become a habit of assuming these things. So G is a graph, it's a planar graph. I have taken an embedding of the planar graph and I have fixed it. Now under that fixed embedding, V is in the middle, the 5 neighbors are in this way. it will be in some way. Let's say it is in this way. So clockwise order, when you write V1, V2, V3, V4, V5, but arranged in a clockwise order around V. Okay? Now you see, there is a possibility that, next is that you should definitely delete this part of the graph, and what you get is like this. So these are V1, V2, V3, V4, V5, right? So these are your graphs, but V is missing now because I have deleted. So this is a smaller graph than G. So this must be 5 color. So in particular, see in coloring, the thing is that if you know the local information, if you know what your neighbors have got as colors, then you can color yourself. You know whether you can color yourself. So if by chance, while coloring, these guys are colored with 4 different colors, then I am done. Some color is repeated. So the worst case scenario will be if these guys get different colors and without loss of generality, let's say 1, 2, 3, 4, and 5. Now I am putting V back to my graph, and I have no option, I cannot color it. So now what should I do? I can maybe try to recolor some of these things, but then if I recolor this one, it has many neighbors, and maybe there some problem will be created. So let us look at only the graph which is induced by the colors 1 and 2. In the whole graph, 1 and 3, let's say. Okay? In the whole graph, there are many colors used, 5 colors used. I'm looking at, so now you have the graph, and you think there is a spotlight only on those vertices and edges. So only on those vertices which has either color 1 or 2. Other side, I don't care. And edges in between. Okay? So of course, you look at, so this is your G, but you are looking at only those vertices which have color 1 or 3. So maybe only some things like this. Maybe also like this. Okay. So it will be a bipartite graph, first of all, and it will be like this: 1, 3, 1, 3, 1, 3, 1. Okay? I want to extend it a little bit. This graph actually may have many components. It may not be all connected, right? So there will be 1, 3, 1, 3. Let's say 2 components. Okay? So the 1, 3s may be like this. And the vertices that I have not drawn, they are exactly the vertices which have got 2, 4, or 5. These as. So if I interchange these 1 and 3s, okay? If I make it 3, 1, 3, 1, these coloring changes has no problem with 2, 4, and 5. And this change has no problem with this guy because they are in different components. So I can take one component of 1, 3 graph and swap its colors. That is allowed. Okay? This is a very, yes? One component at a time. You can do it for 5 components, but one by one. So it's the same thing. But what I'm saying, if I change for one component, then no problem. Okay? So there is a possibility that V1 and V3 are in different components in the 1, 3 graph after you gave coloring. In that case, you just change the component which contains V1. Then what will happen? This will go away and this will become 3. So now you have just 4 colors used here and you can use 1. Okay? But the other possibility is that it is not connected, not in different components. So that means it is connected, right? So what is the definition of connectivity in graph? When do we say U and V are connected? There exists a path. So let's draw a path. So let's say there is a path. Okay? Okay? But you know, the colors of the vertices of this path, it is either 1 or 3. And because of the coloring condition, it should be 1, 3, 1, 3, 1, 3, something like this. Okay? Fine. Forget about this now. I have a path. Okay? But now I have some more things, so I will do it with 2, 4. Now I will consider the 2, 4 graph. If they are in different component, I will change one component and I'll be done exactly like before. Otherwise, they have a path. So let's draw that path. So otherwise, these guys have a path. So 2, 4, 2, 4, 2, 4. Right?
Will it always in even form like 2, 4, 2, 4 not there in the
Yes, because I have taken the graph which has only those vertices that have got the color 2 and 4. G24. Instead of G13, I have taken G24, and inside only I am looking at the vertices which has 2 and 4. So if V2 and V4 are in different components in that graph, then V2's component I will swap the colors. V4's component I will not swap the colors. Still it is a good color. But now I will have 4, 4. So I can color this guy with 2. If not, if they are not in different component, that means there is a path inside the 2, 4 graph. And that path will have colors 2, 4, 2, 4, because you cannot have 2, 2. It should alternate, right? Okay. But now there is a problem, because you see, if I do this, I have taken an embedding. So there is a crossing now. But well, they can cross if 2 of the vertices are the same. But if they are the same vertex, so let's create such a situation. So let's say these are actually the same vertices. This can happen. So it should not cross on the edges, but on the vertices they can. But according to my orange path, the vertex, let's call it X. Okay? The vertex has got the color 4. And according to, so this particular vertex X is on the orange path, so 2, 4 path, as well as the 1, 3 path. So according to the 1, 3 path, it has got the color 3. According to the 2, 4 path, it has got the color 4, which is not possible because my C is a function. It cannot go from 1 to many, right? So it's not a valid thing to happen. Right? Something I'm deducing the color is 3 as well as 4. That cannot happen. So there lies your contradiction. This cannot happen, and that's the proof of the 5 color theorem. Yes?
This is in G minus V or G?
This is in, so first we colored it in G minus V because we can, and then we put back V and trying to recolor the whole graph with 5 colors. Because
it may be possible like okay, V2 to V4 it will be like, it is not going from outside, it is going from like inside only.
no, you draw it and try to do that. So it is like this.
Okay, it will get through this one.
So, and then you have to connect these two. One is inside, another is outside, so it has to pass. Okay? Is that okay? Fine for everyone? Yes? So I will erase and we'll go to the next one. Zin, you want to take pictures? Very good.
I have taken.
Pool. So this one the pool. And the second one. Second one says let G be a planar graph. Yes?
One question is how the minimal counter example was in your proof in the previous proof?
When you build at V,
Yes.
the degree, minimum degree vertex, the rest of the graph is 5 color. Okay. So what we are saying is, so till now what we did that G has a small degree vertex. Okay, if G is planar. But we are going one step ahead. We are trying to say G has one edge whose degree together, so the sum of the degrees of those two vertices, they are small. So I am saying that not only it has a small vertex, but it has an accumulation of two vertices which has small degree. Right? And those things may be very important to know the structure of the planar graphs. Okay, so how do you prove? So, what is my first line? First line is always the same.
Contradiction. Like suppose.
Yes. So, I will not say that it is a proof by contradiction, but usually while writing papers, we will say let G be minimal counter example. Okay, right? So what does it mean? G is a planar graph, but it also has minimum degree 5, but it does not have a light edge. So these kind of edges are called light edge. So it doesn't have an edge in V such that U and V both are small degree. Okay. Now, I define a charge function. Chx equals to, let's see which one I'm using. I think I'm using the vertex one, so degree minus this and all these are simple graphs, by the way. You can do things with non-simple graphs, but so I will do degree minus x, degree x minus 6 for x in V, so Vg, I am not writing the full thing, to degree x minus 6 if x is a face. Okay? This has no reason right now. This is kind of the things we do, and I will explain like how you can start doing this. But right now this has no other meaning. Degree of face is the number of edges around it. Length of the face, it's the same. Okay? For uniformity we write it. So
What is F?
F is face. So, okay, was keeping it, but now. So it is set of all faces of G. Okay. So tell me, right now, how much charge does the vertices have? So I don't have vertex of degree less than equal to 4. So the first one is degree 5. How much charge does it have? -1. How much charge do degree 6 vertex have? 0. 7, 8, they are positive. How much charge does the faces have? The smallest is a triangle. Triangle has 0. 4 face, more, positive. Okay? So only this degree 5, this is poor. So the way I will think about it is that it helps me think like this. There are many ways to think. In fact, you can take the other way around. The function may be other way around. Most of the things are negative and some things are positive. So in this setup, degree 5 vertices are the poor guys. And I somehow need to make them rich. And why do I need to do that? Because of this. So let's say summation charge x and x values over vertices of G, union faces of G. Okay? I'm taking this. Okay? So what will it be? It will be summation degree of x when x is inside vertex of G, right? And then I have minus summation just 6, and this also varies over x is in Vg. Then I have plus summation degree of x, where x varies in f of G. Okay? And then I have another minus, which is just like this. So I will say summation 6 and x, but x varies over faces of G. Yes, yes, 2 times. Okay? So now
we need to write the length of
Yeah, that's
yes, so I'm saying, okay, so I'm saying length of face equals to degree of face. I'm defining it. Yeah? Okay, so now let's do this calculation. Yes?
in second one, x is a face.
Face, yes. So it's a conditional. So summation degree of x when x is a vertex, how much is it? 2 number of edges. So it is 2 times E of G. Okay, good. Then summation constant, this will be 6V. Okay, so 6 Vg. Now summation faces. So it's like you are going to each face counting the edges. But so you will have summation faces, but then each edge is participating in 2 faces, so you have double count. So when you do this, it's also a handshaking lemma, basically. Okay? It's a dual of the handshaking lemma. So you get again 2e, but you already have a constant 2 here, so it will be 4e. So it will be 4 times edges of G. And this one will be, no, this will be
6 into mod f.
6 into mod f. Yeah, that is true. Okay. So we will take 6 common. Actually, we can take minus 6 common. Then I will have Vg minus Eg plus Fg, right? So how much is this? This is Euler's form. examples, and G is connected, right? It's a minimal counterexample. So this becomes minus 12, which is less than 0, strictly less than 0, yes.
Why is there an equality, like degree sum of the faces is equal to 2?
Okay, so
Should be less than equal.
yeah, but G is actually 2 connected, because that I will put as an exercise maybe. Okay. So every such minimal counterexample or critical graph should be 2 connected, because if it is not, I can show you. So if it is not, if it has a cut vertex, what you can do is, you can consider this graph once, color it. You can consider, that's a good question, sorry I missed it. So you color the red graph once, you color the orange graph once, whatever this color is, maybe from the left side it is 1, maybe from the right side it is 1, but then you permute the name of the colors and make both of them one, join it. That will be a coloring of the whole graph, so it will no longer be a counterexample. So minimal counterexamples cannot be disconnected or have a cut vertex, so they must be 2 connected. Once you have 2 connectedness, that equality holds. Okay? Now,
didn't understand this one.
so what I am saying, the minimal counterexample must be 2 connected. Okay? So this I will come back to later. Okay? Maybe in tutorial.
What would happen there? What if one did
So there may be some long edge kind of a thing which is not participating on, if there is a cut edge, for example, it will participate only in one phase. So there will be inequality instead of equality. But now what I know is the whole thing is actually negative. So you can imagine there are many degree 5 vertices. Otherwise, how the whole thing became negative? If there were no degree 5 vertices, then it will never be negative. Right? So somehow, if I, now this is the process, this is very important. Yes.
So this is a minimal counterexample for not having the edge like this, right? Not for the color.
Yes, for the
So
light
how
edge.
is this counterexample?
No,
So color.
no. This one? No. This is for the light edge. You're right. So, yes, you are right. You are right. We may not need, as long as it is negative, we may not need, right? So which direction is the inequality? So
Degree sum should be less than equal to 2.
so it should be less than here, right? It should be less than equal to 2. So I will have a less than equal to here, and I will have a less than equal to here. So it is still negative. Yeah, you are right. Sorry, I gave the example for coloring. Came quite naturally. So yes, but in this context, we may have to do a little more. In fact, we can do it with a maybe cut edge. Okay. Now the thing is, we have this situation, and let's see what kind of things we may have. So let's say I have a degree 5 vertex. Okay. So this is degree 5 vertex V. So let's look at the degree 5 vertex. Actually, let's take a triangulation. Let's triangulate G. So in the beginning only, whatever this minimal counterexample is with respect to number of vertices, actually I have taken a triangulation. Okay? Then this equality problem will not be there. And I will avoid another problem very soon. So now, you see, I have this situation. Okay? I have this kind of a situation. Because triangulation.
So this minimal counterexample should exist in the permutation also?
Wait. 5. So,
There might be more edges, right?
yes. So any counterexample, you triangulate it, it is still a counterexample. because the degrees has increased. Right? In the triangulation, you don't have a light edge. If you don't have a light edge in its subgraph, because degrees has only increased. So I can always think that if there is a minimal counterexample in triangulation, that is also a counterexample in least number of vertices. I am not going into edges. So that's right. Now what happens? Now, actually, if I have degree 5 somewhere, I want to draw two pictures. Degree 5, what will be the degree of, so let's say this is U and this is V. What can you tell about the degree of V? It is at least 7, right? So degree is greater than equal to 7. Okay. Yes? Now actually here I don't need degree. Let's say I just have a graph, just have a vertex which has many degrees. I want to see, because you see, you have to donate charge. So I want to see around V how many degree 5 vertices are there. So what I want to do is, I want to move the charges. Think about money. Everyone has some money, some has negative balance. So if I am rich and my neighbor, means my adjacent guy is poor, I want to give him some money. And after that, after this whole process is done, money has not gone outside the graph. So I will calculate the whole thing again. If it becomes positive now, or greater than or equal to 0, then I have a contradiction. Right? Okay. So that is called the discharging method. That is the discharging process, like giving charge. Yes?
So could you explain why degree of V is greater than or equal to 7?
Yeah, can count it as 6.
If it is 6, then this edge is a light edge. 5 plus 6 is 11. So I have it is satisfied. So I am saying it's a counterexample, so it cannot be satisfied. It has to be at least 7. Now let's say I have taken a V, and let's say this guy, the first vertex, this one, this has degree 5. What can you tell about V2? 7 or more. What can you tell about Vn, or whatever this is? 7 or more. So, how many degree 5 can I have maximum in its neighborhood? How many degree 5 neighbors can I have of V? Degree by 2 floor. It cannot be ceiling, then 2 of them will be. Right? Okay. So it's basically the whatever the cycle is, its independence number. Okay? So from here, what I get, that number of degree 5 vertices in the neighborhood of V is less than or equal to degree of V by 2 floor. Okay? Almost there now. So I can erase this calculation. Right? Yes, please.
Is it necessary like the neighbor of that vertex is a degree 5 vertex? Is it necessary?
No, that's why less than or equal to. But there is an upper bound. That is what I mean. Sorry.
Yes.
Okay? Thanks.
So I'm assuming all of them are neighbors.
Triangulation. I'm assuming triangulation. That's why neighbors will form a cycle. So what I have here is important information is x in V union F, charge of x is negative. This is my important information here. I will keep it. Okay. Now I will do something. I'll put a rule. Rule 1. So usually we write just R1. Okay? R1. So any V in Vg with degree V greater than equal to 7 donates, how much should they donate? So a degree 5 vertex, now think like this. So I'm trying to give some hint that when you do it, how to do it. So for degree 5, I have 5 hands. Okay? And I know none of the hands are poor. They are rich. At least 7. So I want 1/5 from each side to become rich. So in other words, 7 or more degree vertices should give 1/5 to each degree 5 member. So let's say donates 1/5 to its degree 5 members. Okay? This is your rule. So this is the rule that we are using. Okay? Fine? But now there is a small thing. Small thing is that let CH star be the, we call it updated charge. Okay, it has kind of settled down those notions, but still people use different kind of things. But updated charge is kind of standard. With the updated charge after R1. Okay, this is the second thing that I want. So now you have redistributed the charge has moved around, money has moved around, and this, after that the function has changed, the value of the function. So that updated function I am calling CH star. And now I want to calculate CH star. If I can show CH star of x for any x is greater than or equal to 0, then I know the sum is also 0. And that is greater than or equal to 0. And that will be a contradiction, right? So let's do that part.
So 1/5 donate means if you have 7, you are donating 1. So float of 1/5.
We'll see the calculation.
What do you mean by 1/5, donating 1/5?
So you have, how much does 7 have? 7 have 1, charge of 1, positive 1. So you are giving, you have 1 rupee, you are giving 1/5 rupee to your poor neighbor. So, calculation. So this is the last step. Discharging calculation. Okay. Discharging calculations. This is what? This is saying that first you calculate x faces. Nothing changed, right? So CH star of x equals to CHX, which is greater than or equal to 0. From faces, no charge has gone anywhere. That's fine. Now, the second one is degree x equal to 5 for x in Vg. What happened to this guy? For this guy, I have charge star of x equals to charge of x, and it has got 1/5 from five hands, right? from each of the 5 signs, because he has a degree greater than or equal to 7 neighbor here. That we have established before. So this becomes, this is -1 plus 1, this becomes 0.
Greater than equal to.
Exactly 0. It had -1 from each side, it is exactly 0. Now the third, yes,
Like 1/5 you're choosing only because you want to make this.
exactly, yes. And then, but you can not be, you may not be able to choose. This is one easy example. So there are, so even I have done, I think the highest I have done is 5 runs, 5 discharging runs. So, but 5 is a lot. Then the paper becomes 25 pages.
So neighbor of 5 cannot be 8.
It can be degree greater than or equal to 7.
So there you are writing
Yes.
1/5 of what?
Our charge.
1/5. Donate 1/5 charge.
Why you got 5 into 1/5?
Because degree 5 has 5 neighbors.
Oh.
Each of them is giving it 1/5. And each of them can give, will give, because each of them are degree greater than or equal to 7.
So this charge will be at least 5. So can I get CH star greater than equal to CHX plus 5 plus 1, 5 into 1 value? Should be exactly equal.
Say it again, please.
So in the right hand side 5 into 1/5 or greater than 5 into 1/5? Because it can be 8 also, 9 also. Neighbors.
I don't care. They are always giving 1/5.
Even 8 is giving 1/5.
Yes. Degree greater than or equal to 7. So any big neighbor is giving just 1/5.
It's not 1/5 of its charge. If it is 1/5.
Okay, so I understand. Okay. 1/5, 1/5 charge. Yeah. Yes, yes. Yes. No, I think they thought that 1/5 of the charge they have. So just it's the absolute value 1/5. So it is giving points, point. That's it. Okay. So I can draw it. I can draw it. So degree greater than or equal to 7. Degree 5 and it is giving 1/5. Okay. And now the last calculation. Degree, of course, degree, no, last 2 calculations. Degree 6 was 0, it remains 0. Okay. For 7, for x in Vg, okay, charge star of x equals to charge of x minus, because it is giving, how much is it giving? Yeah, okay. Charge star is greater than or equal to, how much, worst case scenario, how much can it go? Degree by 2, 5, right? So into 1/5. So it is degree by 2 into 1/5. Okay? I will do the calculation here, and there I will just write greater than or equal to 0. So the calculation can be, what is the calculation? Charge is degree x minus 6. Then I have a minus degree x over 10. You remember there was a actually there is a floor, but I have ignored the floor. So I am actually counting more, that I am giving more, right? So that is okay. If that works out, it should be okay. So this is 10 and 9 times degree x minus 60. But degree is greater than or equal to 7, so it is 63. So it is indeed greater than or equal to 0. Okay. It's strictly greater, but I don't need in this case. So it is greater than equal to 0. Okay? Yes.
So the neighbor of that V
Yes.
is a 5 degree. The degree of the neighbors can be different. So charge is different.
We don't mind as long as it has degree greater than equal to 7.
So like suppose the charge is T. So
Yes.
or other has a charge T1.
We don't care. So the rule is that if degree greater than equal to 7 has a degree 5 neighbor, degree greater than equal to 7 gives 1/5, exactly, 1/5 charge to degree.
So it will not affect like the degree equals.
Sorry?
It can equally distribute.
I don't want it. I want what works. This works for me, so I can do this. If something else works, it's fine, but I don't need it. Okay? So, in this proof, we are just saying it gives 1/5. Okay, so now what we got is all faces, all vertices, after this discharging happened, redistribution happened, they have greater than equal to 0 charge. So tell me, what is star x? Yes, in a moment. V in F. This is greater than equal to 0. Okay? But summation charge star and summation charge, they should be the exact same thing, because never any charge has gone out of the graph or come from outside. Whatever distribution happened is internal, so they should be preserved. Okay? So that's the contradiction.
What you have written here on the right side, what is it? Degree of x minus.
So this calculation I have done there. Okay. So it is like charge star of x is equal to charge of x actually greater than equal to minus degree x by 2a. Yes. Now the question. Yes.
What is the meaning of giving charge?
So you have money, 100 rupees. You are giving 20 rupees to degree 5.
But
That's
here, what is happening in the field, like realizing ranges.
So you are redefining a function, and this is CH star, that you are deducting 1/5 from your degree greater than equal to 7 vertex, and you are adding 1/5 to your degree 5.
So that is something like changing ages, right? That's how we can.
No. Just the charges. Graph is the same, only the charges are different. You can imagine that they are just you have, so that's why I said think about money, it's easier to think that way. You have 2 rupees, you are giving 1/5 rupees to 20 paisa to 1/5. Yes. Yes. No, but you need to calculate this. So your charge function cannot be whatever you want. It has to, you have to add. So you need Euler's formula to add. So there are in fact 3 types of charge function that you can define on planar graphs. For average degree there is different. I will show 2 examples I guess. So I will write the charge functions here that you can use.
Why it is 1/5?
Because you need to make degree 5 has to become 0. Right? That's the only poor there. So the discharging rules are decided by how you can make all the poor guys not poor. So any questions you please keep asking. Oh, I need a board pen.
What if I have more
I need a board pen.
degree 5 days?
Sorry?
There is you said the degree is greater or equal to 7.
Just a second, I cannot hear.
The degree of that vertex, the total
Yes.
vertex is greater or equal to 7. What if all of them are having degree 5?
No, I showed that all of them cannot. for example, 2 degree 5 cannot be neighbors. Then I already have what I want. Remember the statement?
No, because the graph is triangulated. So every degree 5 cannot have a degree 5.
Charge of x equals to integral x minus 6 for x in V to degree x minus 6 for x in F. So this is the second one is the exact opposite. Do you have another? Yes. So suppose this was 5.5. Okay. So floor is 5. So I was doing something minus 5. Now I am doing something minus 5.5. So I am deducting more. Still it is better than previous. So you see, these are the 3 kinds of functions you have. Mostly these are used, and the first one is called vertex centric, which I used. So faces did not have too much contribution. Second one is exact opposite. For vertex you have twice degree, so degree 3 vertices will be 0 charge, and faces you will have a lot of charge. This is face centric, so I will write vertex centric. This is face centric, and the last one is called balanced. Okay. So what will happen if you add it up? You will get a, because of this minus 4, you will get a minus 4v and a minus 4f, and for this one, because it splits summation degree over v and summation degree over f, it will get again a 4e, and then when you do it, it will be minus 8. Okay? But still it is negative. So the first two will be minus 12, the second two, the last one will be minus 8 if you add them up. So this poor, rich, all these things will be there. Okay? So any questions about this, or I will go to the next example.
So that minimum degree 5 should be there in the statement, or?
That is tutorial. So minimum degree 4, but it becomes more complicated. Yes.
What if we take 1 by 4, like it donates 1 by 4 charge instead of 1 by
Okay, so if it donates 1 by 4, of course, degree 5 is happy. But what happens to degree 7? So degree 7 will give 3 by 4. That is also okay. Yes.
Degree 7 gives 1 by 4.
Yes. So how many? To maximum 3. Okay? Maximum? Yes, because we told that a big degree vertex can have maximum degree by 2 floor many degree 5 layers. That is one key point. If it had to give in 7 directions, then it already will be 7 by 5, and it will become poor because it has only one charge. It will be minus 2 by 5. So that's not good. That's why we have that small lemma exercise that maximum degree 5 neighbors can be floor of this thing. Okay? So 1 by 4 also works.
1 by 3 also works.
1 by 3.
8 for 8.
Yes. 1 by 3 will work.
For 8 we have 1 by 4 now. That's why.
Oh, okay.
That's why that
No, but 8 has 2 charge. 8's charge is 2. So that is okay. So many things will work, it has flexibility. So this kind of a result is actually true when degree is greater than 23. Or maybe in general, I am not sure about that, but degree greater than 23 is. And degree greater than equal to 4 is definitely correct. I gave it as an exam question also, so some delay.
Who started the discharging method?
I think that Hewitt-Kempes things evolved. The 5-color theorem proof, it evolved. That is actually discharging. So you are giving some kind of forbidden configuration. It can also be done in the language of discharging. It evolved, and Apple and Haken did it like for this big thing. I don't know the exact of it. Yes.
In the previous picture, like we were there and it has some degree.
Yes.
Then there is a vertex with degree 5.
Yes.
And they have also neighbors
Two neighbors.
connected to V.
Yes, but that part is not important. They have a neighbor because of the triangulation.
Yeah, if they are triangulated, so there is
Yes,
an edge
it's a cycle. It's a cycle.
Not here, like there is an, like if V has degree 5,
Yes.
then there is an edge between V1 and V2, like their neighbors are
Yes.
right?
Yes. Like this.
Yes,
Okay.
but
So this is V1.
then V2, V3 has their neighbors, like here only in this cycle.
Yes.
Then there is an edge between V2, V3 also, right? And this is triangular.
V2, yes. This is V2, this is V3, there is a edge.
Okay, like V1 has degree 5.
No, V has some, V1 has degree 5, okay.
And its neighbor is V2 and V3.
Yes.
Then there is an edge between
No, not V2 and V3. V2 and, so V2 and Vn. This one.
Okay.
This one and this one.
Yes, so there is an edge between them also, right?
No.
Triangulated means?
No, but it can have something like this. Something like this. Outside. So that is not the whole graph, right? The whole graph is bigger. So it can have connection with the other vertices, which I did not draw. Okay. So, yes.
So I think for like arbitrary alpha, 1 by alpha, I think we can calculate the alpha. For which
What is alpha?
Like alpha, any value I am taking, for which 1 by alpha the charge of the X will become a positive.
No, but what is alpha? I didn't.
Alpha is a number that we have to find for which alpha this charge will become positive. I think we can.
Yeah, but
we
you can do that, but it's just for this problem. There are like thousands, literally, like thousands of problems which are solved using this method, and they are much more complicated. Usually, this is one of the simplest examples. So you have to back calculate at some point of time, but you have to do something that it works. So a lot of to and fro comes into picture. Okay? So the next one, what I will try to do is maybe you guys figure it out. It's a bit easier, but it is balanced. I will use a balanced charge. But what is the time?
9:37.
9:30. So I have 1 hour. What? 9:38. So I have less than 1 hour. So I will not do the next example. It will be in the tutorial, and maybe there I can. Okay? Because I want to. So this is discharging method. The next plan was to do one example for balance. I will not do that. Rather, I will go to the next level. So the first level was Hewitt's proof of the 5-color theorem. Second level is discharging. Now we have a third level from 2016 or something like that, which is potential method. So it is an enhancement of discharging method. So now there are two functions. One is this charge function that you are familiar with, and another is a potential function. But it is usually, I have not seen any example on planar graphs to be specific, but you can imply things for planar graphs. But it is usually with edge density. So let G be four critical graph. Then I will just write E and I will define it there. Minus 3, where E equals to G. There is no face because it's not a planar graph, right? So what I am saying is, four critical graph is a graph which cannot be three color, but any of its proper subgraph can be three color. Okay? So this is the statement. Now this will be good. Let's see how it goes. So I've never presented it in a classroom kind of an environment. So always I have read a paper with someone. So this is a paper from Combinatorial Theory Series B by Kostoshka and Yancey. And the thing is, if you read the paper now and the way I will prove, it's very different, the writing wise. I have tried to simplify it a lot. And also what I have tried is, I have tried to write it in a language, so the potential method is used many times now. So I have tried to use the language in which now it is written. So I have translated it in the usual language that people use. Okay? So there is a format now. Like for discharging, you see there is a format. You give the charge function, you calculate it, find it's negative. You don't do that in paper. Let's say it's negative when you do this. And then you say, what are your discharging rules? No, sorry. Then you say, what are your forbidden or reducible configurations? Like these things are not there in my graph. Like degree 5 has to have a neighbor which is degree greater than equal to 7. And then around one vertex there can be maximum these many. So these kind of supporting structural information you give for your counterexample. Then you use that to calculate, you define your discharging rule, and then you calculate the updated charge and get a configuration. This is the format, right? 4 or 5 steps. So here also there are things like that, but it's not so standardized yet. I will send it. I'll send it. So actually what I will prove is this. But that is enough because E is an integer. So even if it is a fraction, it is okay. Right? It will be greater than equal to C over time. Yes, so what I am saying, if E is greater than equal to 5.5, then it is greater than equal to 6 also, because E is an integer. So I will drop that. So I will prove this and then conclude that with a CD. Okay. So from here, let's do some calculation. E greater than equal to 5V. So I am doing the way you will also, if you want to do research, you will do it. So you want to prove this, let's say, first find your statement. Then, from here, you recalculate. 3E greater than equal to 5, so this is if and only. 5V minus 2. Okay, this is if and only if. Isolate 5V, all these things, isolate these things. So it will be 5V minus 3E is less than equal to 2. Okay? So it's basically the same thing I am writing in this. Your first goal is to write things like this. Something times V minus E less than equal to something. Okay? To prove E greater than equal to some function of linear function. That's it. I don't know for non-linear what. So now you take that 5V minus 3E and define potential of your graph not only one graph, any graph. So I will give a generic name. So let's say Z equals to 5 times number of vertices in Z minus 3 times number of edges in Z. Okay? The rho of Z is a potential function, and the potential function is defined on graphs. Clear? Okay. Now, next is I will restate theorem 3. Restate. So G is for critical implies, actually here is G, potential of G is less than or equal to. You agree? Yes? So I just took this, imitated and gave a definition. Potential, it's called potential. So potential function is not a fixed function for everything. It depends on the problem you are having. So if you want to prove this kind of an edge density, convert it into a potential function. So the reason why it is done this way, you see there is no factor, right? The factor is in the right side. Because I want this to be potential to be an integer. So potential of a graph is an integer. I will use the property of integers that if potential of G is strictly greater than 2, then it is actually greater than or equal to 3. And I think that's why it is used. Okay? So that is... no, that's like that in the paper. Now we are simplifying things, so I hope it will work. Okay? That's it. If it doesn't, then I have to say something in black box. That's it. So first, so this is the first step. Okay? Just restate the theorem. The second step will be to observe things like how it works on small graphs. Let's do some calculation. What is the potential of K1, for example? Can you tell me? You guys tell me. What is the potential for K1? 5. So potential, this I will write small. 5. Then potential of K2, 7. Potential of K3, 6. One more. Potential of K4, 2. Okay, fine. So this is for critical, you know? Right? But it follows this. Just to observe that. Okay. The next step comes, I will still write here, but this is one very important step. So which color other than white is visible? Yellow? Yellow is visible. So the next step is called, it is a popular name. In no paper you will find this. But when we do research, we call it this. So we want to prove something called a gap lemma. Okay? No, sorry. There is one step before that. So we will start the proof. We will start the proof and then do some limits. So, proof of theorem 3. But the restatement. Okay. So, what is my first line? Usual first line. What is it? Yes. So, let G be a minimal counterexample, but I will explain this. That is, G is, first of all, it has to be 4 critical, Okay? And okay, and the minimality is number of vertices. For this proof, I don't mind number of vertices. So first of all, G has to be 4 critical. Okay, it is 4 critical. Second of all, it has to have potential of G is strictly greater than 2, right? But if it is strictly greater than 2, potential is an integer, so I can actually write it is greater than or equal to 3, so I write like that. Okay, this gap of one number is very important. And then I will say, among all such examples, G has the least order, that is the number of vertices. So there are many counterexamples maybe if the theorem is false, but I take something which has the smallest order. There may be many with smallest order, but I know if it is smaller than this, then it is not a counterexample.
So already you mentioned, right? Minimal counterexample.
I know, I'm just explaining what it means by minimal counterexample, very explicit. Because each of these information will become useful. It's a repetition, yes. Okay, next comes the gap lemma. For gap lemma, you will use this side of the board. So the lemmas be here and the proofs be there. So G has potential greater than or equal to 3. For the gap lemma, what I want is, I want that the subgraphs of G will have higher potential. Okay? So somehow I want to show that subgraphs of G, maybe with some exceptions, they will have very high potential. And there is a gap between 3 and that potential. And that gap will become useful. Okay? So I cannot explain every Y right now. So maybe after some practice, maybe. But one focus should also be on how to prove it. Okay? Yeah. Gap lemma always starts like this. Let H be a subgraph of G. Okay? Then we have a few bullet points. So first one is usually potential of H greater than or equal to whatever it was, 3 if H equals to G. Okay? In my case, I have a few exceptions, so I will just write it. And when you practice, you will probably understand why these things happen. If H equals to K1, and third is rho of H greater than or equal to, equal to 5, equal to 6, if H equals to K3, and rho of H greater than or equal to 7 otherwise. So I am saying, unless my subgraph H is the whole of G, or a singleton vertex, or a triangle, the potential is greater than or equal to 7. So there are 3 exceptions to my rule. Okay? This is what I want to prove. Yes? Yes. So everything now happens under this assumption. So this is fixed now. Okay? So what I am trying to do, I am trying to get structural information about my minimal counterexample and finally get to a contradiction. Okay? I will get many informations, they will contradict. Okay? So that's what the goal is. This is a very important information, and this proof is difficult. Okay? I have time. Yes. Okay. So let's see. The first one, is it true? The first condition, is it true? That if G H is equal to G, potential is greater than or equal to 3. That's our assumption. So this is true. Second one is true. Observation. Third one, observation. So if this, so again, what is my favorite line of the proof? A little different. I take a maximal counter example now. Okay? So, proof of gap lemma. And the proof is difficult. Okay? But then once I do the proof, things become easier. 2 more lemmas and it's done. So, gap lemma. Take maximal counter example. Example H. But then I again want to explain what it means. Okay? It's not very easy or immediate. So that is H is a subgraph of G. H is not equal to K1, K3 or G. Okay? This is the next part. And then potential of H is less than equal to 6 because it's strictly less than 7. So that means it is less than equal to 6. Its potential is integer, remember? Okay? And among all such, H has the highest so I don't remember what minimality or maximality criteria works, but I will say number of vertices plus edges. Okay? I will take this criteria. Usually this works.
Should be strictly less than 6, right?
Strictly less than 7. So that is less than equal to 6. Okay? So are you okay with my statement? The assumption. Okay? Basic assumption. Now comes the nice and difficult part also. So let's see. Always have difficulty in explaining this. So this box is G. This small box is H. And you know that H is a proper subgraph of G. So then it must be 3 colored. Right? So that 3 coloring, I will denote something like this. 1, 2, 3. Okay? There will be some more drawing which I will draw in the mirrors. Let me draw one more picture. Exactly like that. 1, 2, and 3. So 1, 2, and 3. Okay? Okay, now small things. If H has only one vertex, then I have already taken care of at 2. If it has 2 vertices, then it is K2 or something with less edge. But less edge means potential is more, because you see in the potential function, it is minus edges. So if you do less edge, it will be plus that value. Right? What happened? No. Okay. So for example, K2 with just 2 vertices, independent vertices, it's 10. Because you have deleted one edge. So K3, If it has 3 vertices, it is K3 or a subgraph. If it is a subgraph, then it is 6 plus 3, 9 or more. But if it is K3, I have already handled here. So I can actually add here one more thing, that number of vertices in H is greater than or equal to 4. This is deduced from our assumption. Okay? Now what I am doing is, I am creating a new graph. This is G prime. Okay? This new graph is, the new graph is, so what I did is, I showed that the minimal counterexample cannot have 3 or less vertices. Explicitly calculated. Okay. So now what I am doing is, I am taking this H, I know it is 3 colorable, I am creating a new graph, and deleting all vertices of H. Instead of that, I am putting 3 vertices called 1, 2 and 3. And on top of that, I need a back pen now. So if there are edges, okay, like this, let's say A, B and C. Then this A, see how was A? A had 2 neighbors in this set which got color 1. I will just put 1 edge here. Okay? But B was like 1 edge with the first color class and 1 edge with the third color class. So I will put 1 edge with 1, 1 edge with 3. And C was like, it had a edge with the second color class, so I will put with 2. So this is how the connection is. If a vertex outside my nucleus has 1 edge with one of the color classes, or more edges, doesn't matter. If it is adjacent to one of the color classes, in my G prime, I will make it adjacent to that particular color. So this is the new construction. Okay? Fine.
So in the class 1 there were say V1 vertices, I got 1 vertex for that.
No, yes. There were some vertices, X number of vertices, but I replace it with 1.
So you're just replacing
the color class, right?
Not really, just replace it. Just think of it, deleting it.
You're just replacing the entire color class with one particular vertex.
Yes, that is a better way. So each color class, I'm just replacing this.
If there is another vertex like D to the first color class, then you
Yes.
have to put an H to D to 1.
Yes. So yes, it's not like any exceptional case. So it will be D and this. Okay, but this is my construction. But do you see something? G prime has less number of vertices than G. Because H had 4 at least, I have replaced it with just 3 vertices. So G prime is definitely smaller than G. Okay. Now one case can be that this G prime actually admits a homomorphism. So admits a color, 3 coloring. So one possibility is G prime is 3 coloring. But then take that 3 coloring here, blow up each of the color classes, and that will be a 3 coloring of G also. So what I am saying is, if G prime is 3 colorable, then G is also 3 colorable.
What about edges between 1, 2 and 3?
There are no edges.
They are different colors, so I don't really care. With respect to coloring, I don't care, because they are different colors. So what I am saying is, if G prime is colorable, 3 colorable, then G is also 3 colorable. Do you agree with that? Then I won't prove it. I will save some time. So I think you can agree with this. So, or you take it as an exercise. G prime 3 colorable implies G 3 colorable. But what does it say? G prime is not 3 colorable.
In G-dash, do we have the edges 1 to 2?
No, we don't.
And if we don't have edges, since G-dash is 3 colorable and 1 and 2 get the same color, then how can
Okay. Yeah, I see. Yeah, actually you can put the edges. So it was not important for the later logic, but you can put the edges. Not. Yeah. So put the edges. And now you get a 3 coloring of G prime. So 1, 2 and 3 will get 3 different colors. Okay, and you can call them 1, 2, 3. So is that okay?
It increases the potential of each.
No, so why are you doing potential? Right now the question is that G prime, if it is 3 colorable, G is 3 colorable. If you agree with that, then I will go to the next. So Sandeep doesn't look convinced.
So how many is I don't know, what is the range?
So if this is 1, the entire color class, we put it 1. So in the coloring of G prime, these 3 vertices 1, 2 and 3, they will get different colors, right? Whatever it represents, you give the same color here, and whatever outside, if there is some color I, you put the same color I here. Okay?
Why they should get a different color?
Because there are 3, it's a triangle. I have made it a triangle, now let me work it out. And if there is a I here, and a J here, which are adjacent, so these 2 are different colors. These will be different colors here also. I've pulled it back. Inside, this one, whichever got this vertex was replaced by 1, right? This is 1 color class, so this is independent. And if there are edges in between, I don't care. So inside is okay. Now inside and outside. If this has got the color, so if there is something adjacent, the problem will be if it gets 2. But it cannot be because otherwise you will have this situation. So we actually proved this.
So you will this color, same color, all of same color, you want to represent as a 1 vertex.
1 vertex. I'm replacing it with 1 vertex. And then making it a complete.
Actually, there exists a vertex in the color class 1, and also there exists a vertex in color class 2. There must be an edge.
No. Doesn't matter. I don't care about it. This may be an independent.
That's why there are 1, 2 edges there.
No, I am putting this. That's it. It's my choice. I don't care if originally there was any edge between them.
What I used to say, if there is no edge, then it will be a same color.
No, but why are you thinking about that?
Okay, no problem.
So it's not coming in the way of the proof, right? You can do whatever you want, but now I am doing this. Am I doing right or not? Just concentrate like that. If I am doing correctly or not. There may be 1,000 ways to do things, but this way is correct.
So G is 3 colorable implies G dash is 3 colorable.
G is never 3 colorable. G is a 4 critical. But now here I get a contradiction that because G is not 3 colorable, G cannot be 3 colorable, right? So that means that G dash is not 3 colorable. Okay? If G dash is 3 colorable, then G is 3 colorable, which is not true, so G dash is not 3 colorable.
Can you just repeat the argument for G dash is 3 colorable?
Can you please take it as it is, because I will not have time, we will do it in the tutorial. Okay? So try to prove it by yourself. It's actually easy, quite easy. So your question is this one, right? Yeah, that you try this. And then G prime is not 3 colorable, means G prime has a 4 critical subgroup, right? So this means G prime contains 4 critical subgroup. It itself may be 4 critical also, but it contains a 4 critical subgroup. So it is like the, okay, now, let's see. Now what if this 4, so here there is a 4 critical subgraph sitting inside G prime. So if the subgraph is it visible, the color? Okay. If the subgraph is entirely outside the nucleus, then the subgraph is entirely outside the nucleus here also. It is basically a subgraph of G and proper subgraph because I have missed the nucleus. That cannot happen. So, because G is itself 4 critical, it cannot contain a proper 4 critical subgraph. Okay. So this doesn't happen. it cannot be completely inside this also. Because this is a triangle, any subgraph of a triangle is 3 colored. So I will erase this also. Now comes the most important part. Maybe you can take a picture, I will modify this picture. The construction is understood, so I will get rid of the violet colors. Okay?
So we have proved that G prime is not 3 colorable. Because
Yes.
G prime is 3 colorable, G is 3 colorable.
Yes.
Right? We know G is 4 colorable.
Yes.
So G prime is not 3 colorable.
No, not it is for
Critical.
critical. Yes.
So now what you are proving? So the
Yeah, so it's, I think it's a bit difficult to get the big picture. So just follow the small steps.
yes, last step was?
I will come to that. So last step was that G has a 4 critical subgraph. G prime has a 4 critical subgraph. And we have said that 4 critical subgraph cannot be contained entirely inside the nucleus because this is triangle. Any subgraph of the triangle is 3 colorable. And entirely, completely miss this nucleus. Because then whatever it is here and it is a subgraph of G, proper subgraph of G. And proper because it's missing the nucleus. So, yeah, now I can use, so it will be something like this, okay? It may contain the full triangle also, I don't know. But it will intersect the nucleus and some part will be outside the nucleus, okay? Now I am going to use a lot of colors and please tell me if you don't see it properly. So, this is something, this part which is outside the nucleus. I like calling it the earlobe. Okay? And the critical graph, where is that? The critical graph, usually I call it critical subgraph. Let's name it something. It's called G double. Bad name, but usually they go with this. So nowadays we write G1, G2. Anyway, so that critical subgraph is G double prime. This red thing, this is G double prime. And this earlobe is nothing but G double prime minus whatever part I have here. Okay? And then I need one more name. So I will highlight this part. So G prime has some part of the nucleus. That part I will call X. I don't know which part of the nucleus, but I will call it X. Okay. Now what I will do is
G double prime is for critical?
G double prime is for critical, yes. What I will do is I will take that earlobe and attach it to this. So this earlobe, remember this is entirely inside G because it's outside the nucleus. So I am taking the critical graph and it's outside, nucleus's outside part, and I am looking at it here. Okay? And next is this entire thing. So the earlobe together with H, I will call it H prime. And this is the interesting graph. Okay? So I will erase this part and go again through this picture because I think it's not easy in the first go.
So X is 1 and 3 on the view.
No, it can be just one. It is at least one or the full graph. It can be anything. It can be anything, but it is not empty. It's just a picture. I cannot draw a very generic picture. So that's it. So I will write an equation and then explain the equation. Okay? By that time you maybe go through that and see how it is. Okay, so once we prove this equation, things will get better. Okay? So let's see. what am I doing? What is H prime? H prime is the earlobe plus H. So what is this earlobe? Earlobe is G double prime minus X, and so the first, this expression gives you that, but not entirely. So at least the number of vertices you can check, right? So potential function is linear on number of vertices and edges. So if I match the number of edges and number of vertices, then it is okay. Or if I have an inequality somewhere, that should be respected. So first I will say that the number of vertices in H, number of vertices in H prime is equal to number of vertices in G double prime minus number of vertices in X plus number of vertices in H. First I will want you to observe this, because this whole thing is H prime, this middle part is H, so it is okay. Now I have to count the number of vertices in this earlobe, that is G double prime minus X. Okay, so number of vertices match.
You're going to prove that inequality or
I am going to prove that inequality. The first step was to prove this claim. So this is my claim. So first I counted the number of vertices. Okay. Now the second thing, count the number of edges. Okay. So I will change this. I don't know if it is equal or not. It's probably not equal. Okay. But let's see which way it goes. So what are the edges inside this entire thing? There are some edges inside H.
Sorry, H
Yes.
prime and H are disjoint?
H prime?
And H are disjoint? Like
Yes. No. H prime is H plus this earlobe.
okay.
Yeah, it contains H as a proper subgraph, because I know this earlobe is also non-empty. Okay. Because the whole G double prime cannot be inside the edges. That we have shown. Okay. So what are the edges? The edges inside H are counted in E of H. The edges inside this earlobe are counted a bit more. Actually, we have counted a bit more. So edges of G double prime, and whatever the edges in the nucleus, we have deducted. So what we have counted is edges which are entirely inside the earlobe and some cross edges. Okay? This we have counted. But now there are some cross edges here also. Right? But two of these cross edges, they might have merged and made only one cross edge. So the edges are more here in H double prime. But if you have more edges, the potential drops. So I can write this inequality. So yeah, for edges it is that inequality. For vertices it is same, and both are linear functions. Potential is linear. So because for edge is with a negative quantity, right, in the function. So this inequality is true. Okay? So any doubts here? This is quite important. Once you have this function. Yes? So I will carry on. Is that okay? Fine. Now let's see. Let's calculate this potential. What is G double prime? G double prime is a 4-critical graph. And it is definitely smaller than G, because I have shrunk G to get G prime. And it is inside G prime. So at least one vertex less, because H have this, and this is just 3, replacing H by 3 vertices. So by my assumption, where is it? Here. G is the minimal counterexample. So G double prime should obey my theorem statement, because it's smaller than G. So it should be less than or equal to G. Okay? How about rho of H? Well, for rho of H I already have an assumption. So it is less than or equal to 6. How about rho of X? Look at the observation. But it is with a minus. So I actually have to see the minimum value of it. minimum value is 5. So I know this is less than equal to minus 5. No, minus 5. Sorry? Row of x is what? X is a subset of the triangle. So into subgraph of the triangle, and I'm coming here until this K3. Okay? So these are the values, or they are more. Okay? If it is a subgraph. So the least value is 5. So least value of potential among all three vertices, among all graphs on three vertices is 5. And that 5 is attained only by K1, nothing else. Okay? So imagine if I had one extra minus 1 from somewhere. Some imagining. Okay? If I had an extra minus 1, then what will be the value? It will be 2. Right? But 2 is dangerous because what is H prime? H prime is a subgraph of G. Now, my subgraph of G, I want to prove it is greater than or equal to 7, and I have taken a maximal counterexample. But H prime is bigger than my maximal counterexample, and it still has less than or equal to 2, which is definitely less than or equal to 6. But there is a possibility that it may be one of these things. It is definitely not K3 because it has 4 or more vertices due to H having 4 or more vertices, not K1 for the same reason. Maybe it's G, but even if it is G, still I have a contradiction because G has greater than or equal to 3 potential, this has less than or equal to 2. But if I don't have this minus 1, then it will be less than or equal to 3. It's a problem.
What about x? X cannot be K2.
It can be. Then I have 7, minus 7, and this is even lower. Then I don't even need this minus 1.
There was K1 is 5, K2 is something.
Now K2 already has potential 7, so it comes here. Okay, it can be K2. Can be easy. Okay, so I need that extra minus 1. So the only case when I need that extra minus 1, if this is equal and that is equal. Okay, so contradiction unless row of x equal to 5 and row of h equal to 6. Okay, so I have a contradiction unless those two are actually equal. If one of them is strict, I'm done. This one I don't have any control over, so I'm not saying it. This much okay? Okay. Now I think I should erase something. No, this is a partial contradiction.
So this arises because of this minus 1 or not?
So if one of them is strict, then I will have a minus 1. Now I don't need that. So if one of them is strict, I have a minus 1. What I'm saying, I have a contradiction and I don't have a contradiction. In that case, this is 5, this is 6. Okay? Fine. Again, the same picture. This is your H.
It's better to write less equal to 3 and then a
Equal
contradiction,
to 3 it will come.
right? Because you are saying unless.
Yes. Okay. So I go back to my first picture. So I'm redrawing the first picture. Okay? I'm just redrawing the first picture. And now see what's going on here. If rho x equals to 5, that means x is exactly monotones. Okay? Now, let me take the set of all, even before that. Let me take the set of all vertices in H which has a connection to outside. Maybe more, but okay. So I am just looking at the vertices of H which has connection to outside H, inside the big graph G. Now, identify those vertices here. Like, look at them. Suppose if they were like in 1 and 2, 1 in 1 and 1 in 2, you see in this calculation, I have not counted this edge. Because what is this calculation? I am counting everything here. No, wait. Just a second. Mm-hmm. No, wait, just a second. So, and here is one more. And this and h prime equals to g. This is important. If this is less than or equal to 3, then also I have a contradiction if h prime is a proper subgroup. So you see here, when can h prime be bigger than h and still have low potential? And low means less than or equal to 3. Only if, so the 3 appears only here. So h prime is also g. So this is the other thing. Okay? Yeah. Sorry about that. Anyways, now what does it mean? Are you okay, Angela? Isn't have a picture?
I took.
I'm going to erase something. So what does it mean? If h prime is equal to g, that means my earlobe is actually the entire graph outside. So if I had a vertex, had a connection here with 1 and had another connection with 2, maybe the same vertex, I don't care, then this particular edge was not counted in my calculation. Okay? Because none of the edges between, so only the edges between x and outside was counted. But something outside x and the edge, those were not counted. So if I now count that edge, then I will have a -3 here. And I'm done. But it's possible that there are no such edges. All the connections are here. That is possible. So that is the only possibility when this fails, the contradiction fails. So, let's say that's the only possibility and this is all the color plus 1. Now I do something, I think this trick was really magical and I just put one edge. Just put an extra edge, okay? Now I may have to look at my notes a little bit. Yes, okay. This whole thing is h. No, h dash is the whole graph now. This is h. These are the vertices which has connection to the outside. And okay, but now that connection, can it be just? There is one small thing. That connection to the outside world set, it cannot be just one vertex. Then it will be a cut vertex. And in critical graphs, we cannot have cut vertex exercise. And so there are at least 2 vertices, and they are independent because all of them have got the color 1 at some point of time. So they are independent. Put an edge forcibly, okay? And now my claim is this, whatever this is, so this guy is now, let's say, h1. My claim is this h1 is colorable, 3 colorable, okay? If it is not 3 colorable, that means it contains a critical subgroup. Okay? If it is not 3 colorable, after putting the edge, it's possible it's not 3 colorable. So it contains a critical subgraph. So inside this I have a critical subgraph. But the critical subgraph must contain this edge. Because this is the only modification I have done. Otherwise it's a subgraph of h and it should be colorable. So there is a critical subgraph here, which I call h3 in any of them. So now let's calculate the potential of h1. H3 yeah, potential of H3. So H3 is some subgraph of some subgraph of G plus one edge. Like if you remove that edge, it becomes again subgraph of G. Right? So H3 is some subgraph of G plus one edge. So what is the potential of H4? So, yes? One second. So H3 you understood? What is H3? H3 is the critical subgraph inside H. It has one edge, right? So I will write. So
What is H1?
wait. So you know H, okay? Call this edge E. H1 is H plus E. H3 is inside H1 and this is 4 critical, and then H3 minus E, H4 is H3 minus E. Okay?
And what was the E?
The edge that I forcibly put
Between?
between two vertices inside the color class of 1. And two vertices which has connection to the outside. Now I am calculating row of H4, okay, which is equal to row of H3 minus E. Don't worry if you don't follow some of the notations, but here I will again tell you. So H3 is a critical graph and it is smaller than G because it is sitting inside H and something. So this is less than equal to 2, follows the theorems. And minus E means plus 3. So this whole thing is less than equal to 5. Now H4 is a subgraph which is less than equal to 5. That means it is either here or there. Okay? Wait. That is a mistake. Because it was a maximal counterexample, this may not be maximal.
Why is row H4, row H3 minus?
Yes? No, I am a bit mixed up here. So let's see. One, and then I'm saying that let's take something which is critical inside, and there was this edge. Then I have removed the edge for critical and now I have H4. No, this doesn't work because H4 should be bigger. A black box maybe, and I will clarify this later on. So what I will say is that suppose, I think I have to get back to this because I'm already over time, but what I'm saying is suppose this H1, so trust me for now, H1 is 3 colorable. Okay? So what I'm saying is, you take that H and put an edge between two vertices which have outside connection and color. And I'm claiming that it is 3 colorable. So if I prove that claim, it will be 3 colorable. For now, think that it is 3 colorable. So this entire H1, so H plus 1 edge is 3 colorable. Okay? So now those two vertices which has outside connection has got different colors. Now you bring them back here and do the exact same process. Okay? The whole thing. And at that time, either you will have px equals to -5, but then you know you have missed one edge counting, which is from 2, or you will have this is something bigger, strict inequality. In either case, you will have 2 here. So that is the -1 that I was talking about. So you will get a contradiction either way, and then this lemma will be proved. Okay? So yeah, then there. But I don't know. I mean, want to continue for 10-15 more minutes and we wrap it up? Or no? Okay.
Some questions actually.
Yes, yes. So let's take a break. Yes. Which one? So, okay. So, a few things. There are a few questions. So first of all, you understood why this is less than or equal to 2, less than or equal to -5, and less than or equal to 6. You calculate the whole thing. This becomes less than or equal to 3. When can, so H prime is a bigger graph than H. Okay? And it has low potential, that is less than or equal to 6. But I have said H is the maximum among all those things. Has highest number of vertices plus edges. So it is contradicting my assumption of maximality of H. I have gotten a bigger thing than H, which still has low potential. Okay? But it is possible if it falls under the first 3 points. But it is less than or equal to 3. So it cannot be 0.3 or 2. It has to be 0.1 or 2. And then it has to be the whole graph G. Now, in that case, your earlobe vanishes and it becomes the whole of G. Because earlobe was the extra thing outside it and it becomes whole. Now, you have some connections from G to outside. If only one, at least one connection is outside 1, then that edge is something I have not calculated. Due to that edge's contribution, I will have a -3 here. And I'll have 0 here. If that is, then it's okay. But if not, that means all the connections are coming from this one. Okay. But then,
First, you have to say H prime is G because it will
yes. Yes. No, but if I have a connection which is not part of this one, then this edge is not counted in whatever I do. If you repeat the calculation, this edge is not counted. Because of this edge, now I count this edge, and then there will be a -3. Because of that -3, this will be 0, and I will get a count. So that means one possibility is there is no connection outside of the color plus 1. But if it is just one single connection, single vertex has a connection, that vertex becomes a cut vertex. And critical graphs cannot have cut vertices. So I must have multiple connections, at least 2. Between two such things, they are independent because they are both in color plus 1. And put one edge and create this H1. And then, which I did not do, is H1 is 3 colorable. Once H1 is 3 colorable, you again go through the same process. But now those two connections are in 2 different color classes. And you have you will have this -3 here if you have -5. So if you have -5, you will have an extra -3. Or you will have a -6 or less. In that case, either way this is less than or equal to 2. And I have a contradiction. And then it contradicts the maximality of H. And the lemma gets. We meet here, that's something unusual there. But everything will be the same. But let's recap, as someone suggested, just a summary. What we are trying to do is, we are trying to prove that if G is 4 critical, then it has a lot of edges through its edge density. Now that theorem, we took it and depending on what we wanted to prove, we wrote a function called a potential function, and that is exactly this 5 times number of vertices minus 3 times number of edges. Next, what we did, we wrote the theorem again. I think the battery is gone. We stated it again that G is 4 critical implies potential is less than equal to 2. Now this is our goal. Forget about the other things. Remember what is potential function? We want to prove this. Okay. We have observed the potential for some small graphs. It comes in handy every day, many times. Next we thought, what if this theorem is incorrect? Let's go by the method of contradiction. So let's take a minimal counterexample. Minimal with respect to number of vertices. So what does it mean? There exists a graph G on 4, I think it's gone again.
Yeah.
Again. So there exists a graph G which is 4 critical but has high potential. Here high will mean strictly greater than 2 and then is greater than equal to 3. And among all such graphs I have taken the minimum one. Okay. Next, I wanted to prove something called a gap limit, which says that any subgraph of G has high potential. And high here means greater than equal to 7. But there are some exceptions. One exception is, what if G is equal to H? Then it is greater than equal to 3 because of our assumption. What if it is a K1? Then it is 5. What if it is a K3? Then it is 6. But again, I know that can one of you just tell? Yeah, see, it's coming and going. So can you please send a message to Chetan or come here to come here and get the battery? Okay. So it is 7, but there are some exceptions, and we also know that these are the only 2 exceptions, K1 and K3, on 3 or less vertices. Others have high potential. You can do it by hand also. So I know if there is a counterexample, that should have at least 4 vertices. And then I got stuck there, right? So because of that, I changed something here, but more or less things will be the same. So what we are saying is, take a maximal counterexample. Just check. This is the usual case. Counterexample H, that is, it satisfies all these things, is less than 6, and among all such H has the lowest changes a lot. I'll not change that. So I will do it in 2 terms, so that will be easier. So I will do something like, first I will prove greater than or equal to 6. Then it will end. Okay? Then I will do 7. Is that okay? I don't No, this is not. Okay. Yes. If there is a chart, you can put it. So, say, no, I'm just thinking, should I put that in the black box for now and then continue? Maybe that's a better thing, and I will do that part, maybe put a note or something. Okay? So, we have all these things, and then what we do is, we take our graph G, we take a subgraph, this subgraph H inside it, so nothing changed. I changed some things and changed it back, so everything is like before. So this subgraph H is there, and this is a proper subgraph of G, because it cannot be the whole graph, because of the first point. So first 3 point actually checks out. So if the counterexample comes, it will come from the fourth one. So as it is a proper subgraph, it is 3 colored. You do a 3 coloring, 1, 2, 3. And you replace each color class by the first color class by the vertex 1, second color class by the vertex 2, third color class by the vertex 3, and make a triangle. And whatever connection was there with the color classes, instead it is now with the vertices, but it may be a little less, because 2 vertices of a color class may be adjacent to the same thing. So that was 2 cross edges. That will be just 1 cross edge with 1. The vertex. And then you observe that if this new graph, which is called G prime, admits a 3 coloring, then I can pull back that coloring and give a 3 coloring of G. That is not possible. So G prime should not be 3 colorable. If G prime is not 3 colorable, it must contain a critical subgraph, 4 critical subgraph, and I am calling that G double prime. But that G double prime cannot be entirely outside the nucleus, because then it is a subgraph of G itself. It's not possible. Critical subgraph, having a proper critical subgraph, not possible. And it cannot be entirely inside the nucleus, because nucleus is just a triangle. Triangle is 3 colorable. Any subgraph will be 3 colorable. Yes.
So G prime is not 3 colorable. That implies G prime contains a 4 critical subgraph.
Yes.
So how is that?
So that is, you keep deleting things until it becomes critical. So now, where was it? Yes. So G double prime is a critical subgraph, and it intersects both inside and outside of the nucleus. It has to. So once that is true, the outside part you are calling it the earlobe. Remember that it is actually subgraph of G, because only the inside nucleus part we have modified. Outside is intact. Take that, copy paste here with H. So take that part and H together. Okay? That bigger graph, so that graph is bigger than H. That is important. That graph we are calling H prime. Now we are calculating the potential of H prime. After we do all the calculation with the, so this equation we have proved, I am not going into that. So rho of H prime is less than or equal to rho of G double prime, which is a critical graph, but smaller than G. So according to our assumption, the potential is less than or equal to 2. Rho of X, it can be 1 vertex, 2 vertex, or 3 vertex graph. The smallest potential you can think of is 5, because of the negative sign is less than or equal to 5. And then rho of H, due to our assumption, it is 6. I don't care about the first one. So if you do all those calculations, what you get is 3, less than or equal to 3. Okay? However, if I have one extra minus 1, then it will be less than or equal to 2. I somehow want that. Okay. But let's see when it is exactly 3. So this and this and this, all these 3 should be equal. Then only it can be exactly 3. Okay. If it is less than or equal to 2, then what do I have? Then I have a graph which is bigger than h, which is a subgraph of G, which has potential less than or equal to 2. But in particular, that bigger graph has potential less than or equal to 6. Okay? So it contradicts the maximality of h, except if it falls under these 3 points. It cannot fall in 1 or 3, 2 or 3, point number 2 and 3, because it has h inside it, and h has at least 4 vertices. These guys have only 3 vertices, 1 or 3. So it must be the first point, but G has potential 3 or more, and this has less than or equal to 2, if there is somewhere there is a restricting point. So that means I got a contradiction and my lemma is proved unless all of these things are equal. So what does it mean by equal? Equal will mean this is minus 5. That means x is only a single vertex. Rho of h is equal to 6. No, nothing after that, but it is 6, equal to 6. And then h prime of h prime, this guy has potential less than or equal to 3. So it is actually equal to 3. And the only time that can happen, because still it is a bigger subgraph than h, so it contradicts the maximality of h, unless it satisfies the first one. So h prime must be G, and potential must be equal to 3, because G, that is another point. That is so potential of h prime is actually equal to 3. Okay? Because G's potential is greater than or equal to 3, h prime's potential is less than or equal to 3, so it is exactly 3. Okay. Now this is the scenario can be handled. That's the thing. So now what we are saying is, so this earlobe is now gone, because h prime is the whole graph. What happened?
Could it be the case 4? H prime is like greater than or equal to 7 case.
No, we are proving this. Yes, it could have been, but then I have already taken h to be the maximal subgraph which contradicts this. But h prime is bigger, so it contradicts the maximality of h. So it cannot fall in case 4 also. Like case 4, it's not falling anyways. It is less than or equal to 3. Okay. So it is not falling in case 4 anyways. Okay.
But how did you prove it is exactly equal to G? Because H prime is not related to G.
No, because h prime is a subgraph of G, and it has potential less than or equal to 3, we have proved. It is bigger than h, so it cannot contradict this. So it must be either K3 or K1, or that also it cannot be. So it can only be the first case. So then it has to be G, basically. Okay. It cannot be a counterexample, first of all, because it's bigger than h. Anything bigger than h cannot be a counterexample to the left, because h is the maximal counterexample. So
then you want maximum with respect to the number of vertices or something like that, not with respect to potential, right?
maximum with respect to number of highest. Yeah, I forgot to. Yeah.
Initially this one.
Yeah. So what I wanted to revert back, because that is a black box. So actually that black box gets resolved if you change some condition, but I don't want to do that now. Okay. So let's see. I will probably do it with this condition. that anyways, H prime becomes the whole graph. And then now if I can find one extra edge that I have not counted here, then I get a minus 3. And then this becomes less than or equal to 0 and I have my contradiction. So I somehow have to find an edge which I have not counted. Turns out if there was an edge from 2 to outside, because the whole of outside is now earlobe, it is an edge between 2 to the earlobe. But that edge is not counted here. Never. Right? What are the edges that are counted? The edges which are inside G double prime. That means here, minus edges of X. That means edges which are entirely inside the earlobe. And earlobe and crossing with X, 2 is somewhere outside. Right? So this edge never gets counted. And plus the edges which are inside H. So this edge never got counted. So if there is an edge with 2, from 2, the color class 2 to outside, that edge never got counted and I can count it now and get an extra minus 3. Okay, and get my contradiction anyways. So,
how do we know 2 is not in X?
Because X is 5 and I have assumed it is 1. Exactly, without class objectivity, let's say it is the color class 1. Okay?
So H prime is all of G now, right?
All of G now.
Okay,
Yes.
so but H prime, how did we get, we took G double prime, everything in the earlobe of G double prime and then added H, and that was H prime, right?
Yes, yes. So the
That
earlobe is now everything.
Right, so then if there's an edge from 2 to outside, then that outside is also part
Outside
of
is also part of G, basically. Yeah.
Yeah.
It's I wanted both pictures. Old
No,
and new.
I mean, what I'm saying is then
Yeah,
you
yeah,
counted
yeah.
the edge, right?
It's not a correct picture, so it is like this.
Right, so the edge is being counted.
No, because you have counted only these kind of cross edges which are with X.
Oh, I see. Okay.
Because you are counting the whole, every edge in this G double prime and removing the edges which are entirely inside the X.
Okay, okay.
So you are counting only the cross edges between 1 and the earlobe. But 2 and the earlobe, 3 and the earlobe, we have not counted. So if there is an edge, I'm happy. I get this and minus 3, extra minus 3. But now I'm forcing that edge. How? I'm saying, suppose there is no edge from 2 to outside and 3 to outside. All the edges, all the connections are from 1 to outside. I know there cannot be just one vertex which has all the connection. Because then it will be a cut vertex. So at least 2 are there. Between those two, forcibly I will put an edge. Okay? Because G is critical. So critical graphs cannot have cut vertices. Okay. So basically it's like this. So you take color, you take this color, you merge them. So the whole thing will become color. So now I'm forcibly putting this edge, and now I have the whole H, the initial subgraph, and one edge. Okay? And this so this is the part I will not do now, and skip and do later on, black box. So this is 3 colorable, turns out. Claim is that this is 3 colorable, this claim let it be paid.
G including that edge or only H including that?
H including that edge. Okay? H plus that edge. That is 3 colorable. Once you do a 3 coloring of this, you remove the edge. This also remains a 3 coloring of H itself. But this 3 coloring, if you come here, corresponds to those active edges, like those who have connection to outside, staying in 2 different color classes. Right? So now you do the calculation again. Just repeat. And if you repeat it, you will never arrive to the situation what we did. And there will be even if we arrive, there will be an extra minus 3. Okay. So we will have something like less than equal to 2 here, which will contradict the whole maximality of H. So H prime is bigger than H. It has low potential, so it should be one of the top 3 cases, but it is less than equal to 2, so it cannot be any of the top 3 cases. So gap lemma gets proved like this, except for that. That I will clarify sometime later, as a note. But is this okay? I think not entirely, but overall, is this okay? That this gap lemma gets proved. Yes.
So when you have that -3, the potential is less than or equal to 0.
Yes.
Then what is the
So H prime is bigger than H.
Okay. Again,
It's a subgraph of G.
okay. Which has
Contradicts
potential
the
less than
maximum.
X. That
Maximum.
Okay.
Yeah.
So these two connectors,
Yes.
so that's why there are these two edges from 1 to outside.
Yes.
So now you draw an edge between them. There can be more than 2 edges also, right?
Yes.
So I would have so many edges.
Yes. But they are all counted if they are from 1. So I need at least one edge to be connected to 2 or something. Okay. So now I have lemma 2. Which one of you can prove? So I'm saying this diamond graph. So K4 minus 1H. This is not a subgraph of my minimal counter example G. Can you prove that? Don't think. So the proof is 1, right? Okay? No, of course not. No, but as a subgraph. G can have this as a subgraph, right? Why not? So tell me, what is the potential of this guy? What is it? 5, right? So is it 5? 4 times 5 is 20. Minus 15, it's 5. Now look at the gap lemma. Any subgraph of G, unless it is the whole of G, of course it cannot be whole of G because this is not critical, it's 3 colorable clearly, or K1, not K1, or triangle, not triangle, then it should have high potential, greater than or equal to 7, it's not. So I don't have any 2 triangles in the graph which share an edge. It's very strong. Okay? I do not have, in the entire graph, I do not have any triangle which share an edge. So this lemma gets proved. So it will be almost impossible to prove that this kind of a configuration is forbidden or reducible in discharging method. It's absolutely impossible. It's extremely strong. Okay. And there is no condition on the degree of the vertices. It can be anything. Just this cannot be there as a subgraph. Okay. The third thing is, third lemma. Okay, I think in the previous tutorial there were many things, but there was one problem in the beginning which says that if you have a K critical graph, then the minimum degree should be K minus 1 greater than or equal to K minus 1. So I can say that G doesn't have a degree 2 or less vertex. It starts from degree 3. Right? Okay. So let's say G has a triangle. At most, one among X, Y, Z can be degree 3. Okay? So I'm saying in a triangle, the 3 vertices, 2 of them cannot be degree 3. Maximum 1 can be degree 3. So you remember the philosophy of discharging, poor people should not be together, right? Very, very close. So I have to somehow separate the poor. Okay. So that's one way of doing it. In a triangle, 2 degree 3 vertices are not there. So suppose not, proof. Suppose they are entirely pictures. So suppose I have a triangle X, Y and Z, and then let's say degree of X equals to degree of Y equals to 3. Let's say this happens. All degrees are 3. These two, there are 2 vertices which are of degree 3. So, of course, degree 3. 2 degrees already taken care of here, so I will draw the other one. It's like this, A and B, right? Can they be the same vertex? Can they be the same vertex? No, because they're not. We create a diagram. No, anything. Because I said subtract. I did not say induced here. I'm using this right. Here I never used induced. I'm also deleting edges. Everything is allowed. That's why I'm saying it's very strong. Okay. Okay.
So what if it is a K program,
yeah,
to lie inside G, right?
It cannot. Yeah.
Okay.
It cannot be because it's critical, for critical itself. So G cannot properly contain K4. So in this case, you can deduce that it is induced, but the statement doesn't say induced. Statement just says that it is cannot. There is no subreference. Okay. So we have this kind of a situation. Now what we do is we will put an edge if it was already not there between A and B. Okay? And next I will do something more. Yeah. I will remove this part of the curve, X and Y. So I will remove X and Y. So from my G, I am just deleting 2 vertices, X and Y. Okay? So if I remove it, and then if it is possible to color the entire graph, the rest of the graph, then what happens? This gets some color, let's say 1. Okay? These two gets some distinct colors. So what are the combinations? 1, 2, 2, 3, 3, 1. Or it cannot be 1, 1, right? So it may be 1 and 2 or 3, but then I put things back and I will put 3 here and 2 here. So color.
This AB edge was not there in
I put it.
initial.
Now I am trying to show that. No, if it is 3 color. So I am not claiming that it is 3 color. Okay. I am saying if the new graph, after adding AB and deleting XY, if that is 3 colorable, I am trying to show that I can extend the color. That's all I am doing. So one option is that this is 1 without loss of generality. These two may be 1 and 2. In that case, I will put 2 over here and 3 over here, and I can color the entire graph. So I can extend the color. If it was 2 and 3, then I could have put 3 over here and 2 over here and extend the color. So those are actually the only 2 cases with some symmetry. So what I can say is, if I can color the graph, so this is G, this is G, if I can color G star, which is G minus XY plus AB. This is like, if it is not there, then I can take this. If it is there, then I don't do it. So if I can color G star, then I can 3-color G also. This is what we can see. Okay? So that means G star is not 3-color. Okay? And it also means this AB edge was not there to begin with. Because if it was there, then how did we get G star? Just by deleting 2 vertices.
If G star was 3-colorable, G was 3-colorable.
Yes. So how did we get G star? If this edge were already there, just by deleting 2 vertices, that must be colorable, right? Yeah. So I know that this edge was not there to begin with. Anyways, that is not the important point, but what I know is G star is not 3-colorable. Okay? And now, so if something is not 3-colorable, what can I say? It contains a 4-critical graph. But the 4-critical graph must contain this edge also. Otherwise, it is just a subgraph of G. And in fact, a proper subgraph of G, because you know, my G star doesn't have 2 vertices of G. So G star itself is a proper subgraph of G plus 1 edge. So my critical subgraph must contain that edge. Okay? So I must have something like this. I mean, I just wanted to say it contains this edge. Okay? And this something I call it G star 1. Okay?
So,
Wait.
that could also you already be present in G star, right? And if it is proper.
This edge is there. Edge is extra. AB edge is not in G.
It may or may not be, or it must be.
I mean, if it may or may not be, but you have to think that.
If it is already in G, then still it is a
Yeah.
subgraph, right?
Then still it is a subgraph, so it was not in G. That you can conclude also from there. But it's not very important. It's important that G star, you can definitely now say that AB is something that we put. Otherwise things already get contradicted. Right? We are always trying to get to the difficult cases, worst case scenario. So if AB I have forcibly put, and then I get a critical subgraph which has this AB. Now I want to calculate the potential of this guy. So G1 star minus E minus AB. Okay? Plus minus 3. So G1 star's potential is G1 star minus this edge.
G star minus.
So G1 star is what?
G1 star is this critical 4 critical subgroup. No, G1 star is correct. So
No, potential.
Minus AB, something minus AB. What minus AB?
G1 star. G1 star. Yes. G1 star minus AB. So what is that problem? So G star is because I did this, right?
Yes.
Okay. So G star is my G minus 2 vertices plus 1. It is not 3-colorable. Okay? It has a critical subgraph. I have to give some name to that. That name is G1 star. That must have the edge AB. Now I am removing that edge AB. Okay? And that is this. I did not give a special name for it. So I am trying to calculate the potential of G1 star. So G1 star is G1 star minus AB and plus 1 edge which contributes to minus 3. But how much is this potential of G1 star AB? Go to your lemma. No. This is a subgraph of G. This is a subgraph of G. So this guy is a subgraph of G. and it doesn't have one edge, it has at least two vertices. So, first of all, this guy cannot be G because X and Y are outside. First case not possible. Second case not possible, it cannot be K1 because it has at least two vertices. I'm just removing the edge AB. So AB and it cannot be K3 because it is not complete. It has two independent vertices, AB. I've removed the edge. So it must be greater than or equal to 5. So it must be greater than or equal to 5 minus 3, that is greater than equal greater than equal to 7, yeah, and greater than equal to 4, okay? Now G1 star, I'm saying, is a critical graph which is strictly smaller than G but has potential greater than equal to 4, which is not possible because G was the minimal counterexample. So G was the smallest 4 critical graph which has high potential. Yes, but it has less number of vertices. X, Y are limited. So minimality is with respect to number of vertices. So it is smaller than G, but it has high potential. That is not possible. So here we get a contradiction. And this lemma gets proved. Okay? So we started with a triangle. 2 of its vertices have degree 3. But then we show that we modify this graph a bit, add one edge, get something. If it is colorable, then the original graph is colorable, which is not possible. So this is not colorable. Then we get a 4 critical graph inside it, calculate its potential, and I get a contradiction, the minimality of it. So I proved that lemma also, last lemma. Okay?
So this G
Yes.
is again the minimal graph.
Everything is happening under the minimal. We are still proving the theory. Everything is happening under that. So G is fixed. G is never changed. Yes, before I do this.
Why G1 star minus AB cannot be K? G1 star minus AB cannot be K.
Cannot be K3 because G1 star has A and B, both vertices, and not the edge AB. So, not XY, but you have both the vertices present in G1 star minus AB, but you do not have the edge AB. So in K3, there are 3 vertices and all the edges. You are missing one. That's it.
Just one thing.
Yes.
So after proving G star is not pre-colorable, this implies it contains the 4 critical
Which has to contain the edge AB. Otherwise, it's simply a proper subgraph of G. From there, we calculate what is the potential of this 4 critical subgraph. Using gap lemma, we get that it is very high. It's not possible. Okay. Okay.
Any K colorable graph, I can get a K critical graph by using edges.
Yes. That is now. Lemma 3 is
Lemma 3 is already there. Lemma 4.
lemma 4. So suppose there is a edge in G and both endpoints are degree 2. Okay? We want to say then X is part of K3. So basically, X is part of a triangle. This is what I want to say. So there is a edge, both endpoints at degree 3, and I want to say each endpoint, each endpoint is part of a K3. So what is the proof?
We just proved that first one thing with degree 3.
Yes, but this is different. I am saying that a degree 3 vertex has to be part of a triangle under certain conditions. This was that a triangle cannot have more than one degree 3 vertex. Now I am saying degree 3 vertex must be inside triangle, but under some condition. Okay, so how does it look like? This is X, that is Y. I am not writing the entire Y, and U and V. Okay? Now from here, I am changing this graph again. Okay? How I am changing is Y, X, but then I have actually made this UV, I have merged it. Okay? I have merged it. Sorry? Say that again.
There is an edge between UV and X.
UV and yes. No, I was just thinking why can we do this? Why can we merge this? There is two edges, but I will do this. Okay. And so anyways, I have merged UV. If there is a loop, I delete it. Maybe there is no loop, but I don't care about that right now. And then I have deleted XY from my graph. Okay? So what did I do? I took this structure, merge UV, deleted XY. So what I get... Sorry?
If UV is adjacent, we are already there, right? Because X is part of K3, so they must be non-adjacent.
Right.
Yes, right. Good. Yes. Thanks. So, yeah, if it is part of K3, we are done. Or otherwise, we merge it and do this and delete X and Y. Okay.
And Y may have same
So, whatever is
neighbor as
this,
X.
no, it can never have because X.
Then you got to get
So if you have, then it will form a triangle, and it's not possible because you cannot have this. Yeah, that's actually a good question. So next is the same drill again. If this is 3 colorable, you go back here, that is also 3 colorable. You put 1 and 1 here, like this will be something, this will be 1. You put 1 and 1. And okay. And then you know there is something over here, right? I should have drawn these words. Something over here. They will have some color combination. Whatever it is, you can extend it. See it, I mean it's like 4 or 5 cases and you can check. There is 1.
Now Y
2
Y
and
cannot
3,
have
then it will be 1, and then it will be 1.
So why in having proper color we should have the U and V of the same color?
Because here, whatever color you have, when you open it, you keep the same color. There is no edge. So you keep the same color. And with the outside, it is always conflict free. Right? So whoever is neighbor of U is also neighbor of UV. Whoever is neighbor of V is also neighbor of UV here. So I know that in neighborhood of UV there is no 1. So in neighborhood of U and neighborhood of V there is no 1. so I can put 1, 1. And then this gets some color, 2, 3, or 1, 2, 1, 3 maybe. So if it is 2, 3, then you put 1 here, and 2 or 3 here. Done. If it is 1, 3, then you put 2 here, but 3 here. And you are done. Okay? So it can always be extended. So that means this is not 3 colorable, and it has a 4 critical subgroup. Right? Repeat of the same answer. Yes.
So why cannot have both the neighbors same as x, but if it has one of them is common, then we form a triangle and x is part of the triangle.
Yeah, so these 4 must be distinct. These 4 must be distinct. Yeah. That's using the matrix. Okay. Now, it is not 3 colorable, means it has a critical subgraph. But that critical subgraph must contain this merged vertex UV. So whatever you modify in the graph, do it small and make sure your critical subgraph contains that small. So it actually contains some critical subgraph. So let's again call it G star. Okay? And now I'm doing, so this is G star minus UV plus U plus V. So what does it mean? I have deleted this UV from G star. Actually I have opened it UV and plus X. So outside I will put X. So what did I do? I took the G star, there was a merged vertex UV, I separated them like before, and added X and made them adjacent to UV. So potent, and this whole thing I will call it G1 star.
So the different X. Different X?
No, the same X. It doesn't, yeah, it's the same X. It matters a bit, it's the same. So, but now let's calculate this potential of G star 1. But G star 1 is a subgraph of G. Because I have merged, from G I have merged it, I have opened it and included X. I did not include Y. That's very intentional. Okay? So what happened? What changes happened here? In G star, from G star it was UV, merged vertex. I've opened it up, so I have got 2 vertices instead of 1, so that is plus 1, and X, so plus 2. I've gotten 2 extra vertices, so it is this plus 2 vertices. I have also got 2 new edges, XU and XV. So I will put 2 edges. But what does it mean? It means row of G star plus 10 minus 6. Okay? Plus 10 comes from 2 vertices, 5. This is minus 3, so minus 6. So this is basically plus 4. And how much is this G star? It's a critical subgraph. Yes, exactly. It is less than or equal to 2. It's smaller than G. So you're getting the whole of it. Nice. So it is less than or equal to 6. So it cannot be the 4th case. G1 star is a subgraph. It cannot be the 4th case. Can it be K3? No, because it has U and V, which are not adjacent. It has 3 vertices at least, U, V and X, so it cannot be K1. Can it be G? Y is not there, so it cannot be G. So I have a contradiction, and my lemma is proved. Okay? Fine, I have all the lemmas now. Do you see the proof already? Last step. So I will tell you how to define the charge function. Look at the potential. Okay? So charge function is always whatever the edge is, you put that times t. And minus twice of this pi. So minus 10. Okay? And this is for all x in vertices. V of g. So I have defined the charge function. Again, we are doing discharging, right? We had some practice with discharging already. Yes? Yeah. So edge times degree minus twice coefficient of vertex. Okay? Why? You will see now. This you can actually understand, realize why it is so. So 3 times summation degree x minus summation 10 x in v x in v. So this becomes 2e. So it becomes 6e. I will take minus 2 common, then it will become 5v minus 3e, which is exactly my potential function. And this I am doing it for the minimal counterexample g. So this is less than equal to. So no, this is
Less than or equal to minus 4.
no.
Is equal to minus 6.
Minus 6. But is it less than equal to?
Yes, because it's greater than you are multiplying by a negative number.
Yes, right. Minus 6. So you have to, G has potential greater than equal to 3. So it is, I'm replacing 3 here, but it is negative, so the inequality reverses, is less than equal. So that means the whole graph is actually poor on charge. And now we do not have the faces, only vertices. Now let's see, who is poor? Degree 2 is not there. Degree 0, 1, 2, not there because of criticality. Minimum degree is 3. How much does it have? Minus 1. How much does 4 have? 2. Okay. Now, how much did you say?
4 is equal to 12 minus 10 to.
Yeah. So R1, every degree greater than equal to 4 vertices donate half charge. So absolute value of the charge is half to its degree 3 neighbor. Okay? Now because of lemma 3 and actually lemma 3 and 4 combined, we know that x and y, a degree 3 vertex is part of a triangle.
Shall
And
we,
yes.
just a sec, he has to change the memory card if it's okay with you to give him 1 minute.
Okay.
Okay,
Yes, but so I have now given a charge function on my minimal counter. Now I will move the charge and I will use the lemmas to conclude that after moving, all charges are greater than or equal to 0. But before moving, using the potential function, I have calculated that the sum of the charge is less than 0. Okay. So,
yes.
okay. Thank you. Okay. Now, if I am a degree 3 vertex and part of a triangle, this is a triangle, but I know these two are not degree 3 vertices. These two are 4 or more because of my lemma 3. So I am getting half from here, I am getting half from there. What is my charge now, new charge? 0. Because my charge to begin with was 3 times 3 minus 10, minus 1. So now I am getting half and half plus 1, my charge is 0. Okay. Now look at the 4 vertex. So 4 vertex is giving half in 4 sides. So it is giving a total of 2. Right? But 4 had 2 to begin with. So it is 0. Look at the 5 vertex. It has 5. Okay? And it is giving away 5 by 2. Right? Okay. So if you go on, like it's quite easy that. So the updated charge, if you call it CH star, then of degree 3 vertices it is 0. Charge of 4 vertices is also 0. Charge of k vertices, it is equal to 3k minus 10 minus k by 2. Right? So you do that, it is 5k minus 10. 5k minus 20 by 2, sorry. Yeah. So it will be 5k minus 20 by 2. Just do the calculation. Okay. Yes. 3 times 2, 6 minus 1. So I can erase here. So degree of x equals to 3, then charge of x is equal to charge of old charge of x plus 2 times half. Okay, but it may get from 3 sides, so I am giving greater than or equal to. This is 0. Then degree x equals to k and some k greater than or equal to 4, let's say. Then I am calculating the charge. So charge of updated charge of x is greater than or equal to old charge of x minus, maybe it is giving in every side, okay, worst case scenario. So k by 2, and this is charge means 3 times degree, that is k minus 10 minus k by 2, 6 minus k, so 5k minus 20, which is greater than 4. Okay? For k greater than or equal to 4, this is always greater. So now, after redistributing the charge, my whole graph has positive, non-negative charge. So the sum will be non-negative. Okay? And then I will have a contradiction that my charge based on the potential was negative to begin with. So that ends the proof, except for that one black box. Okay? So,
lemma
lemma 2 for lemma 3. So, the so I had taken, what if x and y both have degree 3, then they have two edges like this, they cannot be the same. Yeah, because I want to put an edge between them.
And also some parts of the lemma 4 also we have used.
No, it's lemma 2, lemma 3 and then lemma 4. Yeah. Oh, in some parts of lemma 4 we have used lemma 2. Yes, yes.
Because
X and Y cannot have a common neighbor. That's true. No, actually 3 is enough. Because X and Y, if they have common neighbor, then they form a triangle which has X and Y. It's not possible. So that's the proof of this guy. I have bad news. So Groch theorem as a corollary of this, then the set is complete. But it's like really 3-4 lines. Okay? 2 pictures. But if you have questions here now about the overview, there may be many small details that you have questions with. So I can answer. Yes?
There was a graph that you drew with a triangle and there were some A and B vertices. In this proof, the second
yes.
Second
Yes.
So now if you have a coloring of A and like the C prime, then how can you get the coloring of C?
Okay, this I can do it with you afterwards.
Okay.
Okay, so it's just case analysis. You delete the xy and then you have a coloring of the rest of the graph, let's say. So any combination of colors.
But then you need to take care of the other vertices also. That might
X and Y are degree 3 vertex. So these are all their
exactly
vertices.
degree 3 vertices.
Yes.
Okay.
In lemma 2, lemma 3, we wanted to say that at most 1 degree 3 vertex. So we said that what if we have 2 degree 3 vertex, X and Y, and then we did the rest.
Okay, exactly degree 3.
Yeah.
Okay.
Then it's okay. Anything else? Okay. So the USP of this paper, other than proving the Orr's conjecture, Galai conjecture, so this proved the k equals to 4 case of Galai conjecture and Orr's conjecture, and then it gave a very short proof of Groch theorem. And it's really short. Okay. So what is Groch theorem? Triangle free planar graphs are 3 colored. Okay. In other words, you can say there are no critical graphs which are triangle free. 4 critical graphs which are triangle free planar. Right? Okay. Because if you have a triangle free planar graph and you cannot color it with 3 colors, then it has a subgraph which is 4 critical. And that is also triangle free planar. Now, your graph looks like this. It's a planar graph, right? Something like this, but it doesn't have a triangle. So it has many, many faces. What if all the faces are 5 or more length? So suppose there are no 4 faces. Okay? It's a very strong thing to say, but that is case 1. Suppose all the faces are 5 faces. Then what do you have? You have, so faces, I'm counting the rings. So through the faces, 5, but maybe I have undercounted because some faces are bigger than 5. So this is less than equal to 2e. I plug it in the Euler's formula, which is v minus e plus f equals to 2. So this will be v minus e. I will change this f. So instead of f, I am doing something which is bigger than that. So I am doing 2e. So that's why the greater than equal to sign. 2e by 5. Yeah, 2e by 5. So what will this be? Below it is 5. 5v minus 3e greater than equal to from here what I will get is 5v minus 3e greater than or equal to 10, which is not a 4 critical, which cannot be a 4 critical graph, right? Because of my theorem. The theorem says that potential, if it is a 4 critical graph, the potential must be less than or equal to 2. It's not that. So, not so if all faces are 5 or more, then I'm done. But of course, the bottleneck should be, if it is a, if it has a 4 cycle. Actually, I will draw the 4 cycle in this way. So x, y, u, v. Then what they do is very smart. So they say, if I merge x and y, and I can color the whole graph, okay, then I can take it out and color my original graph, right? So if I identify these two vertices, identify them, still the graph remains planar. Why? Because this is inside a face, so I can make a fake edge and contract it. If I can color this graph, I can decontract this edge, delete it, and x and y will have the same color. But there is one catch here, and you did not tell me. So after contracting, maybe you create a triangle. So it's no longer a triangle-free planar graph. Right? That's possible. It's possible, right? Okay. So if you do not create a triangle, then things work out fine. Okay? But what is the case when you actually create a triangle? You will create a triangle after merging two things, x and y, which were separate before. So you create something like this if you had something like this. Okay? So let's say you have that bad case and you have something like this. No, that I don't mind. That I don't care about, because this is a 4-phase, so that's my problem. But now, UV cannot have a path through them. So there is no path between U and V from outside, because if it has a path, it has to go through these two vertices. And if you add this, you create a triangle. Or if you add this, you create a triangle. So no UV path from outside. So in particular, there is no this kind of a path, which will, if you merge UV, create a triangle. So maybe
we're talking about planar graphs.
Triangle-free planar graphs. Yes. So instead of merging, so either you can merge xy. If you cannot, that means there is something like this.
Why can't you draw that inside that
Face, right? It's a face.
It's a face. Yes. I have taken a planar angle. So it's face. It's outside. Yeah, it's a good question, but because of that. So, but now you have no problem in merging U and V. So you merge them. Now what you have is a triangle-free planar graph. So minimal counterexample again. This. So you have gone something under minimal and then put it back.
Can you just read the last?
Sure. Do you agree with the edge here? Another. Okay, what kind of? If that graph is colored, then again that is a 3. Okay, I'm doing exactly, but I'm making after merging, after contracting, it any triangle. Of course, it will stay planar. The only possibility it creates a triangle. It doesn't create a triangle. Then by induction, smaller. So exactly what I'm doing. I'm saying let's merge x and see if it's right. If it does, that means and it is outside because in space nothing is. I merge. It doesn't create a triangle. For that, to create a triangle, there should have been a path from outside. That cannot be planar and triangle. Okay. That's the proof of gross theorem using this. So it
Can we use this right here?
Yes. It must have a surface, then I'm done with the theorem. If it has a surface, then I'm done.
Okay.
Otherwise, Gauss theorem was a very big,
So I teach a lot of things in undergrads, but even for I think MTech in eyesight for Herman, I did not teach this Gauss theorem. So it's quite important. And in fact, whenever someone comes up with a shorter proof or an alternative proof of Gauss theorem, it's a very excellent proof. So, okay, thank you. I'm sorry for keeping you for so long.